Hello, my name is Amrit Madugundu, and today I'll be presenting Nessie, an NESL compiler, on behalf of my teammates Dhruv Gupta, Neal Menon, and Siddharth Peyyeti. So first, what is NESL? NESL is a first-order data parallel function language designed by Guy Blalock. It supports data parallelism in two ways. One, through an apply to each construct, and two, through a set of parallel primitive operators such as reductions, prefix scans, and permutations. This makes NESL a natural fit for irregular parallel algorithms that cannot be easily expressed in lower-level data parallel languages. For example, as can be seen in the function below, square_sequence squares the elements in a given sequence. It is also possible to map an expression containing multiple variables or multiple sequences of the same length. So coming to the Nessie compiler. The Nessie compiler translates NESL source code into CUDA through a series of program transformations. It was developed by Lars Bergström, Advai Poduturi, John Reppy, Nora Sandler, and Joseph Wingerter. So why do we need this compiler? The modern GPUs today are advanced enough to handle extensive data parallel algorithms equipped with their several cores and processors. However, most of the GPU programming till date is done using low-level languages like CUDA and OpenCL. These do not allow the programmer to reach the full capability of the GPU. These languages do not require the programmer to perform quite a few kernel calls. NACL programming language provides various parallel level constructs. These languages are unable to handle the Nessie compiler, which converts the NESL source code to CUDA C code, which can then be further used. Hence, we implement a wide range of optimizations which can be hand-coded in the GPU programs today. The Nessie compiler also comes with a basis library. The basis library defines all primitives available in the surface language. These functions are written in NESL, but can access certain constructs that are not available in the surface language. These functions need to be able to directly manipulate segment descriptors. Segment descriptors are used to describe the nesting structure of sequences. For example, the underscore vector construct allows basis functions to decompose a sequence into a segment descriptor in data. The basis functions may also use base type case and poly type case constructs to define the behavior on different types. So coming to the architecture of the Nessie compiler. The architecture of the Nessie compiler comprises of 8 phases. 1. Parse or type check. 2. Monomorphization. 3. Normalization. 4. Flattening. 5. Optimization passes. 6. Shape analysis. 7. Fusion. And 8. Code generation. Let us discuss each of these phases more in depth. So first we have the parsing pass. Here, the source code and basis library are read by the compiler and an abstract syntax tree is generated, or AST for short. The type checking pass then ensures type correctness. This representation makes an instantiation of polymorphic functions explicit. Next we have the monomorphization pass. This instantiates all monomorphic functions to monomorphic types as needed, hence eliminating all base type case and poly type case constructs from library functions. We do this by specializing the type case constructs that are used in the NESL basis library to the actual type arguments. This produces a monomorphically typed AST. The third phase of the Nessie compiler is the normalization pass. The normalization pass simplifies the program. It has namely 2 tasks. 1. All non-atomic expressions are to be either lead-bound or tail-bound expressions. 2. Tuple unpacking is eliminated by introducing an explicit projection primitive. The fourth phase of the Nessie compiler is perhaps one of the most important phases. As GPUs cannot execute nested parallel operations directly, flattening transformation is used to map the NESL program source code to a SIMT execution model. SIMT stands for Single Instruction, Multiple Threads. The flattening transformation eliminates apply to each constructs. Flattening converts nested data parallelism into flat data parallelism. the nested arrays are transformed into segmented arrays, which are flat arrays paired with segmented descriptors. After flattening the code, the program is converted to an intermediate representation, which is called flan. In flan, a sequence is decomposed into two parts. One, a flat base sequence, and the second, where one or more segment descriptors encoding the nested structure. For example, the NESL array 378 will be represented as shown, where the first string represents the segment descriptor and the second string represents the base sequence. The fifth phase of the Nessie compiler is optimization phase. The flan programs produced by the flattening transformation could be translated into CUDA without much additional modification. However, the result would be inefficient. The most significant issue is that every parallel flan primitive would become a single CUDA kernel. Flan optimization. Several standard optimizations. Shape analysis. Once the flan intermediate representation is optimized, the compiler performs shape analysis to determine the size and structure of arrays. A shape parameter has a unique ID and an optional concrete value. A shape parameter may determine a variable's length or its value. We only attempt to determine the concrete values of a sequence or segment descriptor in two cases. One, when we know it contains only one element, or two, when we know it is uniform. Let us consider the following nested sequence, 1, 2, 3, and 4, 5, 6. The sequence represented by flan will be as shown. The first string, this outer segment descriptor will have the shape VEC 1, 2 because it has only one value and that's 2. In the second string, this inner descriptor will have the shape uniform underscore VEC 2, 3 as it has two values and both of them are 3. In the third string, this will have a shape VEC 6 unknown as it has 6 elements but all are not equal. Fusion. This is the last step of the optimization phase of the Nessie compiler. Code generation. The last phase of the compiler is code generation. This phase is not yet fully implemented yet. Coming to the strengths of the Nessie compiler. Nessie is a new NESL compiler built from scratch. It is designed to support better fusion. The backend transforms flattened code to CUDA in several steps, and it is but a test bed for future optimization experiments in vectorization avoidance, piecewise execution, and blocking. The Nessie compiler has been a breakthrough for parallel programming in modern GPUs. However, there have been quite a few areas for the Nessie compiler to improve. Fusion, segment descriptor management, and memory management are major limitations for the Nessie compiler. However, it is very difficult or slightly impossible to support these improvements. The NESL language, which is the program source code for the Nessie compiler, was designed for wide vector machines. The output of the compiler, CUDA, is a parallel computing platform and application programming interface model designed by NVIDIA. It allows software developers to use a CUDA-enabled GPU for general-purpose processing. There is a ton of work planned